Welcome to this deep dive into the heart of calculus and decision-making, optimization. Have you ever wondered how an architect determines the strongest shape for a bridge? How a logistics company like FedEx finds the most fuel-efficient route? Or how a trader maximizes profit? At the core of all these questions lies a simple yet profound mathematical condition. The derivative must be zero. Today, we will demystify why f prime of x equals 0 is the magic key to finding the maximum of a function. To understand optimization, we first need to visualize what a derivative actually is. Imagine you are hiking up a mountain. Your position is x, and your altitude is f of x. The derivative f prime of x is simply your instantaneous slope. If f prime of x is 5, you're climbing steeply. If it's -2, you're descending. Mathematically, the derivative represents the rate of change. In the real world, this is the speed at which your profit grows or your energy consumption changes relative to your input. Now, imagine you reach the very peak of that mountain. At that precise summit, for one tiny moment, you are neither going up nor going down. You are standing on flat ground. Geometrically, the tangent line to the curve at this point is perfectly horizontal. Since the slope of a horizontal line is 0, it follows that f prime of x must equal 0. This is the first-order necessary condition. It's the universe's way of saying, to stop increasing and start decreasing, you must pass through 0. Let's look at a concrete business example. Suppose a company like Apple or Tesla is calculating its profit function, P of x, where x is the number of units produced. Profit is revenue minus cost. To maximize profit, they don't just produce infinitely, they find where the marginal profit is 0. Statistical data shows that companies using calculus-based optimization can increase their operational efficiency by up to 15 to 20%. When p prime of x equals 0, the cost of making one more unit is exactly equal to the money earned from it. This is the sweet spot of maximum gain. Optimization isn't just for business, it's the law of physics. When you throw a ball into the air, its height follows a parabolic path. At its maximum height, its vertical velocity is exactly 0. This is Fermat's theorem in action. Pierre de Fermat in the 1630s was one of the first to realize that the extremum of a function occurs where the rate of change vanishes. Without this principle, we couldn't calculate planetary orbits or design the trajectory of SpaceX rockets. However, there is a catch. Finding f prime of x equals 0 only tells us the ground is flat. It doesn't tell us if we are at the top of a hill, a maximum, or the bottom of a valley, a minimum. To distinguish them, we use the second derivative, f double prime of x. If the second derivative is negative, the curve is frowning, concave down, meaning we found a maximum. If it's positive, the curve is smiling, concave up, and we are at a minimum. In data science, this is crucial for gradient descent, the algorithm that trains artificial intelligence by minimizing error. In summary, the condition f prime of x equals 0 is the fundamental starting point for solving the world's most complex problems. From NASA's trajectory calculations to the algorithms that suggest your next favorite movie, optimization ensures we get the most out of our limited resources. By finding where change stops, we find where greatness is maximized. References: 1. Stewart, J. Calculus Early Transcendentals, the gold standard for optimization theory. 2. Nochettel, J. and Wright, S. Numerical Optimization, for advanced algorithmic applications. 3. Chiang, A. Fundamental Methods of Mathematical Economics, for the business perspective.